Okay, second question. Here we have a not super complicated, but a complicated system here where we have two masses that are being pulled downwards this way due to gravity. We have T1, which would be the tension just between these two blocks. We have T2, which would be the tension of these two blocks being pulled this way. We can argue, since we're not worried about this having any sort of mass or moment of inertia or anything, that T2 here and T2 here are the same, right? And then we have the force of gravity acting on big M over here. Now, question A. Just ask for a free body diagram. So this is mass M, so this is representing this guy here. Oh. So this guy here. So, come on. So this guy here has force of gravity acting on little m. He has, yikes, T1 that way. Forgive me. He's got T2 acting this way, and Fn acting that way. Over here, we have force of gravity acting on big M. And we have T2. And that's it. A is reasonably simple. Now, one thing we have to remember for B1 and 2 is the fact that it blatantly tells us the system is in equilibrium. If it says equilibrium, that means that the net force is 0. Now, it's asking for the force T2 exerted on the block of mass M by the string, express it in terms of M, theta, and physical constants, which is most likely going to be G. That's a theta. Okay. So, I'm going to look at the system, and I'm going to say, let's just look at this part. Probably the easiest way to do this. So we have T2 acting upwards, and we have the force of gravity acting on all 3m of this mass, the 2m and the m, parallel, acting against it. And the argument is still that the net force is 0, so the acceleration is 0. So when I create my net force equation over here, I'm going to say T2 minus, so I'm letting up the hill be the positive direction, T2 minus 3m, all three of those masses, all 3m of that mass, times g. Now, remembering that the force of gravity parallel to an incline is force of gravity sine theta. So this is force of gravity sine theta equals, well, 0. So, a little bit of simple math, we get T2 equals 3mg sine theta. Okay. Now, 2. The mass big M for which the system can remain in equilibrium. So, the biggest mass basically that 3m can be, or this m can be, so that it still stays in equilibrium. So this is a slightly different argument. Erasing this picture for a second. Now we basically have all of this mass pulling this way. So we're going to say that the force of gravity acting on all 3m in the parallel direction is going to be just counteracted by the force of gravity m. Okay. So, force of gravity due to big M minus force of gravity of all 3m parallel equals 0. Or we can look at it as we're looking for the situation at which these two things are just equal to each other. Okay, so we get force of gravity on big M, force of gravity of the 3M. Okay, so we got big M, G equals 3M, oh, sorry, 3M, little m, G, sine theta. Cancel out the G's, and big M is equal to 3M, 3 little m, sine theta. Checks all our boxes, right? We can have little m, we can have theta. Now, we're getting into C. C changes things up a little bit. It says, now suppose that M is large enough to descend so that the sphere reaches the floor before the blocks reach the pulley. Answer the following for the moment immediately after the sphere reaches the floor. Okay, so let's go back and look at our picture here. So they're talking about immediately after this guy goes thunk and hits the ground. So after that happens, there's no forward driving force anymore. So when it says, does T1 increase, decrease to a non-zero value, decrease to 0, or stay the same? Well, the answer is it goes to 0. Oh, it goes to 0. And very simple reason why. The net force is 0. Both blocks at that instant in time are traveling upwards with the same speed. There's no longer an acceleration because the net force is 0. So if there's no net force, there's no force acting between these. There's no force of this thing pulling on this thing because there's no force of this thing pulling on those things. Okay. C2. Is the velocity of the block of mass little m up the ramp, down the ramp, or 0? Well, that could be also a pretty easy, straightforward question because right beforehand, the acceleration was positive. It was up the ramp. So that means right beforehand, the velocity was positive. And there hasn't been enough time for, the force of gravity acting on these to slow it down going up and start pulling it down because we're talking immediately after that block hits the ground. Okay. Is the acceleration of the block of mass m up the ramp, down the ramp, or 0? Well, once this is no longer driving it up forward, it's going to start to slow down. If it starts to slow down while moving uphill, that means the acceleration has to be down the hill. So we're going to say down the hill. And your argument really could be that from this point on, since there's no forward force, the acceleration is going to just be some component of g. So this, arguably, would be the acceleration down the hill. Now D. D brings in friction. Always fun. So consider the initial setup in figure 1. Now suppose the surface of the incline is rough and the coefficient of static friction between the blocks and the inclined plane is mu static. Derive an expression for the minimum possible value of m that will keep the blocks from moving down the incline. Express your answers in m, mu, theta, and fundamentals, which will probably be g. So now we're going to sneak all the way back to the picture. So here we are. Now, let's look at this. We have force of gravity, right? So we got force of gravity parallel due to those two masses. Now, if they're trying to move down, then the force of friction acting on both of them is this way. And then we have the force of gravity of this guy acting that way. Okay. So we're looking for the minimum possible mass. So we're going to say we're still looking for the situation where the force of gravity this way is exactly equal to this combined with that. So we're going to say force of gravity parallel of the two of them, negative, down the hill. Now, friction, weirdly enough, because they're trying to slide down the hill, is up the hill, so I'm going to make that positive. And this guy, nope, no, I was right the first time. We're setting it equal to mg. So we're looking for the situation where the force of gravity pulling downwards on this guy has to be exactly equal to the combination of those two forces. You really, yeah, let's just leave it at that. Okay. So this is going to be negative 3mg sine theta plus mu static normal force equals big M G. Okay. Now, normal force isn't one of the things we can use. But if you remember, going all the way back to our picture here, anytime we have one of these incline questions, the normal force, this guy or this guy, or if we looked at this as one big combined mass of 3m, is just the force of gravity perpendicular, which is Fg cos theta. Okay, so now we come back here, and we're going to say minus 3mg sine theta plus mu mg cos theta equals big M G. Okay. Now, if I'm going to write that up here, let's say mg. Now I'm just going to flip-flop these because I don't really like the way it's written. So I'm going to say mu mg what? Nah, let's just leave it the way it was. So we got this. So now we can cancel these guys out. If you really want to, you can factor something out. You can factor out the m. So you can say, oh, sorry, there's a 3 in here. So you can factor out the 3m and leave this as minus sine theta plus mu cos theta equals big M. Okay, last question. String connecting block M and sphere of mass M then breaks, and the blocks begin to move from rest down the incline. The lower blocks start a distance of d from the top. Okay, so it's going to accelerate that way. So the acceleration acting on these guys is going to be based off of F equals, oh, not F sub MA. F equals MA. Now, F now that they're going downhill, we're going to have, let's for the hell of it, let the acceleration now let downhill be positive. So we're going to say F is going to be equal to force gravity parallel minus force of friction. And that whole thing is still equal to ma. Okay? If that's the case, and we're going to say mg sine theta, or really 3mg, because it's the whole set of masses, right? Because this guy's also here. 3mg sine theta minus mu 3mg cos theta equals 3m a, because now we're only concerned about this big piece moving, so it's 3m, and we're looking for the acceleration. So I got 3m, 3m, 3m. So now my acceleration is just g sine theta minus mu static g cos theta. Or if we want to factor that out, we could say A is equal to G sine theta minus mu static cos theta. Okay. Moving down. Now we have to find out the velocity at the bottom. So the block, the lead block, is moving a distance of d. Starts at 0 and has an acceleration that we just found. So we're going to use kinematics. We're going to say vf squared equals vi squared plus 2ad. We're looking for vf squared. It's said that this starts at 0. 2. A is that big, not so pretty thing that we just came up with, which was g sine theta minus mu static cosine theta times d. Do the square root of both sides, get rid of the squared, and your answer is just vf equals 2g sine theta minus mu static cos theta d. So, while it's a little bit tricky, and it's obviously a little bit of algebra, wasn't all that terribly difficult. So hopefully this helped. If you guys still have any questions about the way I did things after you look through this, by all means ask me, let me know. Because as I say a million times, we have to make sure you guys know how to do this. I don't really care in terms of what the grade comes out to be. I want to make sure you guys can do this so you can do well on the test. All right? So I will talk to you guys later in the week. I will be posting other assignments for you later in the week. So let's keep positive, let's keep working on this, and let's do this.